Hello, class. The topic of this video is something called a binary de Bruijn sequence, which is something pretty cool, and I've written down the definition here for you. So what is a binary de Bruijn sequence? Well, each of these things has a degree associated to it, so we'll call the degree k. And it's a length 2 to the k circular binary string. So that means that when I write down the string, I'm going to write it in a circle, or if you want, you can write it straight and just realize that the last bit in the string connects up to the first one. So it doesn't have a start or end. You're just sort of meant to imagine it looping over and over and over again. And what I want this string to have is that if you follow the string around, that every length k binary string occurs exactly once. Okay. So I'm going to give you examples of these things of each degree up to 3. So here's one for degree 1, namely 0, 1. As I read around this circle, there's a length 1 string, and there's the other length 1 string. These are the only length 1 bit strings of degree 1. Note it has length 2 to the 1, which is 2. Okay, that's a very, very, very boring example. Let's see a slightly less boring example. Let's see one of degree 2. Okay, so I claim that this is a binary de Bruijn sequence of length 2. Okay, so note it has 2 squared, which is 4 bits in it. Okay, and what are the 4 length 2 bit strings? Well, they're 0, 0, 0, 1, 1, 1, and 1, 0. And if you look at these, you can read them off. There's 0, 0, 0, 1, 1, 1, 1, 0. And if you kept reading around again, you just repeat through these same strings. Okay, and so this is all 4 of them. If I want to do degree 3, then I can do this with 0, 0, 0, 1, 0, 1, 1, 1. So this is my length 8 string, and so if I read this off, then I'm going to read it off onto another sheet of paper. So if I go ahead and read off the length 3-bit strings here, then I start with 0, 0, 0. There. And then I get to 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 1, 1, 1, 0, 1, 0, 0. And you can check. There are my 8 possible binary bit strings of length 3. And they're all encoded here in this degree. They're all encoded here in this degree 3 de Bruijn sequence, which has 8 things. And of course, you can see, why does it have to have length 2 to the k? Well, because there's 2 to the k binary strings of length k. Okay, and so I did 1, 2, and 3. So now you might say, okay, well, could I go and just do 4? And well, you could, but it would take you a bit. Because this is a not obvious condition. In fact, if you thought about degree 3, you might take a bit to come to this realization that you have to have this kind of thing in it. Okay. And in fact, actually, it's not at all obvious, even, if you think about it, that I can do this. So maybe for degree 4, it turns out it's not possible. Or maybe it's possible, but there's only one way to do it and it's hard to find, or who knows. And then what if I go up to a really large degree? Like, what if I talk about a degree 100 de Bruijn sequence that should have some ridiculous length? Is there even one? Who knows, right? And so here the central question for us is going to be, is there a binary de Bruijn sequence of length k for each k? Okay, So you might recall on the very first day of class that I said that combinatorics was the study of structured arrangements. And I said that sort of depending on the structure, you might ask the question, how many arrangements are there? Or you might ask the question, what do the arrangements look like? How do we find them? Or you might even just ask the question, is there one at all? And so we're sort of now at the phase where between this and talking about Eulerian trails and circuits, we're really at the phase where we're talking about just the question, does there exist a binary de Bruijn sequence of length k at all for each k? Now, there's a particular way to interpret this, and this won't surprise you, as being a graph theory question. And so I want to show you what that graph looks like for k equals 4. Okay. Now, you might ask, okay, for k equals 4, how many vertices is the graph going to have? Well, probably it's not going to have 2. So then you might guess, okay, it's probably going to have 16. It would take you a while to guess, but the correct answer is it's going to have 8. And the 8 vertices are going to correspond to the strings of length 3. Okay, so here is the vertices of our graph. And what I want to do here is I want to think about how I'm going to make a length 4 string of bits out of 2 length 3 bits. And basically, the way I'm going to do it is to say, okay, well, I could go from 0, 0, 0 and link up those 2 zeros with those 2 zeros and then join a 1 to it. So actually, I'm going to associate an edge here, and this edge corresponds to the length 4 string 0, 0, 0, 1. These are the first 3 bits. These are the last 3 bits. Likewise, this edge is going to correspond to the string 1, 0, 0, 0. Again, these two line up there. Now, you might notice immediately that I'm drawing arrows on these edges because the order actually matters. I get a different string if I go 0, 0, 0, 1. In fact, actually, it doesn't even make sense to go from this vertex back to this vertex. But I could go from 0, 1, 0 to 1, 0, 1. And actually, I could go from 1, 0, 1 to 0, 1, 0. But notice each of these edges corresponds to a different length 4 binary string. This one corresponds to 0, 1, 0, 1. That's that edge. And this one corresponds to 1, 0, 1, 0. That's that one. Okay. I'll be back in a minute once I have all of this filled in. So here this is with all of our edges filled in. And I'm claiming that each edge corresponds to one of the length 4 bit strings. So keep in mind there are 16 of those, so there should be 16 edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And that's a plus because we know how to handle Eulerian stuff, which means visiting every edge, albeit we're going to have to think a bit about what we're going to need in order to find an Eulerian trail going through this mess. Okay, but we'll get there. But I want to note before I do that, this I've also allowed an edge going from a vertex to itself, because in order to capture the string 0, 0, 0, 0 and the string 1, 1, 1, 1, I need that edge there and that edge there. Okay, so now let me try to convince you that if I make an Eulerian cycle in this graph, that corresponds exactly to a binary de Bruijn sequence of degree 4. First of all, before I convince you of that, what does an Eulerian circuit even mean in a directed graph? And the answer is that you have to visit every edge, but you have to visit every edge in the direction that it is indicated that you're supposed to. So you're supposed to go this way along this way along this edge, and so on and so forth. Okay, so why would one of those correspond to a de Bruijn sequence of degree 4? Well, the answer is each edge corresponds to one of the length 4 bit strings. And so if I start here, for example, with 0, 0, 0, and then go here, then I'd add a 1, and then add a 1, and so on, each edge sort of describes one of these and puts them all in a circle. And as long as I get back to where I started, then I indeed get this circular string that, like it's supposed to, hits each of the length 4 strings. Now, you might ask, well, how do I know if there is such a thing or not? We don't really know the Euler's theorem equivalent for directed graphs. But actually, if you think back, for a directed graph, what did I need to be true? Sorry, for an undirected graph, what did I need to be true in order for there to be an Eulerian circuit? I needed every vertex to have even degree. And if you thought carefully about why I needed every vertex to have even degree, if you think back to the proof from 2 videos ago, that was because every vertex had to have the same number of what I called in edges and out edges. Namely, you had to enter and leave every vertex the same number of times, because otherwise you got stuck there. So that condition translates rather naturally to directed graphs. Namely, what you need is not that the degree is even for every vertex. What you need is that every vertex has the same number of edges pointing into it as the number of edges pointing out of it. The so-called in degree has to be equal to the out degree. So if you want, this vertex here has in degree 2 and out degree 2. And then this vertex here also has in degree 2 and out degree 2. Okay. In this weird situation, this vertex also has in degree 2 and out degree 2, because this edge from this vertex to itself counts as both an in and an out. Okay, so if you go back to our proof of Euler's theorem and replace graph with directed graph, replace every vertex has even degree with every vertex has in degree equal to out degree, and replace connected with you can get from anywhere to anywhere else by following the arrows, so-called strongly connected is the technical term for it, then the proof works just the same way. So I don't need to reprove Euler's theorem. Basically, we can do exactly the same thing, which is to bounce around, make a random-ish path, and then check that if we aren't done yet, we can sort of stick in various pieces. Okay, so let me write down for you a path. Okay, so we're going to start here, and the first thing we're going to do is go around this loop, and then we're going to go down here. Okay, so I've labeled the edges here so that you can see this, but just so that you can follow along, I'll do it real quick with the marker. So start here, loop around here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And we knew there were supposed to be 16 edges, because the 16 edges were supposed to correspond to the 16 strings. And so that should give us a binary de Bruijn sequence. And so let's really quickly make sure we can translate that to a binary de Bruijn sequence. Namely, if I go ahead and try to translate that to a binary de Bruijn sequence, what binary de Bruijn sequence do I get? I get the binary de Bruijn sequence that starts 0, 0, 0, and then 0, then 1, 1, 1, 1, 0, 1, 1, 0, 0, 1, 11, 12, 0, 13, 1, 14, 0, 15, 0, 16, 0, except you realize at that point that actually we were done at this point. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is 16 bits long, viewed as a circular string, remembering that this ties around to here. And so if you read off all the length 4 things, it starts 0, 0, 0, 0, and then 0, 0, 0, 1. Okay, so if you write out, as I just did, all 16 of the length 4 strings, you should see that you get every length 4-bit string exactly once. And all we needed for this to be true was that this associated graph was strongly connected and had in degree equal to the out degree. Okay. Now, if you wanted, you could make the associated graph for k equals 5 or k equals 6 or k equals 20 or whatever you want. And you can convince yourself it's always going to be strongly connected. That's not so difficult. And you can convince yourself that it is going to have always, in fact, every vertex will have in degree and out degree equal to 2. Why? Well, if you think about it, what is the in degree? The in degree corresponds to the strings that end with the same 3 bits that this vertex starts with, or k-1 bits in general. And the out degree is the ones that start with the same k-1 bits that this ends with. So, for example, if you wanted to imagine we're in the k equals 6 case, okay, then our vertices correspond to length 5-bit strings. And so, say we're looking at this vertex, you can ask yourself, what vertices go into this vertex? Well, the vertices, they have to end with 0, 1, 0, 1 in order to go into this vertex. So that vertex and this vertex, those vertices both go in here. Okay, and those are the only 2 vertices that can possibly go in here, namely the ones where I prepend a 0 or a 1 to this 0, 1, 0, 1. Okay, and what are the 2 vertices that come out of here? Well, they have to start with these 4 bits, so they have to be 1, 0, 1, 0, 0, and 1, 0, 1, 0, 1. And so those are the 2 vertices that correspond to the out here. Okay. And so the in degree and the out degree for any of these graphs, from k equals 1 up to k equals 3000 or higher, however high you want, they're always going to have in degree equal out degree equal 2 for every vertex. And so it's always going to be possible to come up with this. And so then our theorem is that there is always a binary de Bruijn sequence of each length. Okay, so we've proved would be a generous term, but we've outlined a compelling proof of this. You would have to really carefully write down the proof of the Euler's theorem for directed graphs. You'd have to slightly more carefully write down the proof that the in degree is equal to the out degree is equal to 2, and the thing is strongly connected. But all of that you could fill in without too much work, and you would have proven this theorem. Now, here's a case where people actually know a lot more than this. In fact, we actually know the number of binary de Bruijn sequences of each degree. So the number of binary de Bruijn sequences of degree k is precisely, and it's precisely 2 to the 2 to the k minus 1. Okay. Which is a number that sort of could not more leap out at you as saying, okay, well, there's some combinatorial argument where I make a binary choice repeatedly. In fact, how many binary choices do I make? I make 2 to the k minus 1 binary choices, then I get this. But, in fact, the only known proof of this involves generating functions and analysis. No combinatorial proof is known of this result, which is nuts. Okay, so a lot of times before, I've sort of said, like, oh, there's not going to be a super nice combinatorial proof of this because the answer has some form that's nasty or has e's or pi's or something in it. Here, this could not look more like it comes from some very clean combinatorial argument, and who knows, it probably does. But if it does, no one knows. All right. I'm going to wrap up talking about binary de Bruijn sequences there. And in the next video, we're going to talk about Hamiltonian cycles. And that's going to turn out to be shorter because it's going to be something that we can say much less about. But until next time, be well.